So let's talk a little bit about numbers and how we think about numbers from a chemistry perspective. We categorize numbers in science in two specific ways. The first is an exact number, and that is a number whose value has no uncertainty. It is exact. So for example, when we say that we have a dozen of something, there's no inexact nature to a dozen of something. A dozen is always 12, regardless of whether it's a dozen eggs, a dozen remote controls, a dozen pens. It all means the same. A dozen means 12. It's exact. When I'm counting students in a classroom, there's not a decimalized student. The number of students in my classroom is an exact number. An inexact number is a number that has some degree of uncertainty, and it's very, very important. I put this in bold here, is that any measurement will have some uncertainty. Anytime you're taking out a device and measuring something with it, there's always going to be some level of uncertainty. The level of uncertainty is dependent upon the tool that you're utilizing to measure the material. Let me give you an example. So first, we need to figure out which of the following contains an exact number. Again, I'll give you a minute to think about this. First part here says the thickness of a sheet of paper is 0.0045, the size of a paper sheet is 8.5 by 11, and the number of sheets of paper in a ream is 500. So think, which of these have to be measured and which of these do not have to be measured? Take a moment, come back, and we will give you a response. All right, so hopefully you figured out that part A here, answer choice A, thickness of a sheet of paper, that is something that is measured. You would measure that with a ruler, a very, very tiny ruler, but you'd still measure it. The size of a paper sheet is 8.5 by 11. You'd measure that as well, but the number of sheets in a paper in a ream is 500. You can't have a 500.1 or 499.5 sheets. So the number of sheets of paper is considered the exact number here. So again, think about, do I have to go through and measure it, or do I not have to go through and measure it? Now again, any measurement has some level of uncertainty. That is one of the key points of this lecture. Much of this has to do with the tool being used to measure, and some instruments are going to be more accurate than others. One rule that we utilize in chemistry in terms of our writing down of these numbers is we always estimate one digit beyond what we can accurately measure. So let's take a look at the difference between the two measured properties, or the two measurements on the right-hand side and what we've reported here. So take a look at ruler A. Ruler A has increments of a single centimeter. What that means is that I can accurately determine that ruler A measures that block somewhere between 3 and 4 centimeters. Then what I do is I estimate one digit beyond what I can accurately measure. I can accurately say that is 3 point something. That last digit is going to be estimated. So if I look at the ruler here, I notice that it's closer to 4 than it is to 3, so I'm going to estimate 3.7. And take a look at ruler B here. Ruler B has the same markings as ruler A, but marks one decimal point beyond what ruler A does. So I can use this ruler and say, hey, that block is somewhere between 3.7 and 3.8. Each of the small little markings in between 3 and 4 represent 1/10 of a centimeter. So what that means is that I can accurately say that that block is somewhere between 3.7 and 3.8. Again, I estimate one digit beyond what I can accurately measure. So making sure that we measure things properly and write out the correct number of figures is something that's very, very important in the world of chemistry. So when reflecting on that, the second measurement is more precise. It has less uncertainty in it because the device that we're measuring measures in smaller increments, and that makes it much easier for us to get a more accurate or precise reading. Every measurement taken must include one digit beyond what can be accurately measured. So I'm going to leave you with this question here. It says, what would be an accurate reading of the beaker on the right? Think about what each of the increments represents and what you might estimate as a number for the amount of liquid in that beaker. Let's assume that the volume is being measured in milliliters, all right? Take a moment, work with that, and we'll come back and answer the question. All right, so hopefully what you notice is that the increments on the beaker go up by 10 milliliters at a time. So I can say that that is somewhere between 40 and 50 milliliters. So what I'm going to do here is I'm going to estimate the last digit. So I see that it's much closer to 50 than it is to 40, so I would venture to say 49 or 48 milliliters. Again, I'm estimating one digit beyond what I can accurately measure. I can accurately measure that that is somewhere between 40 and 50 milliliters, so I estimate the ones place digit. We refer to all of the digits in a measurement we know, plus the uncertain digit, as significant figures. Now, this will prove to be much more important when we start doing math with chemistry. But if we don't make the measurement, we need to follow a set of rules to determine what digits are significant and what digits are not. So if you're given a number, you need to be able to determine how many significant figures are in that number. So let's take a look at a couple of rules here that we use to determine whether digits are significant or not significant. Sometimes we refer to them as significant digits, sometimes significant figures. The first rule here says that in any measurement, non-zero digits are significant. So if the number is not a zero, it is considered significant. So 123.4 grams would have 4 significant digits. The other rules involve the location and placement of zeros, whether they occur before the number, in the middle of the number, or after the number. Zeros between two non-zero digits are significant. So for example, 101 would have 3 significant figures. The first one, the 0 in between them, and the 1. So I'm counting up each digit and determining whether it is significant. For step 3 here, it says leading zeros, those at the beginning of a number, are never significant. So for example, 0.00101 would have 3 significant figures. The 2 zeros in front of the number are not significant. Remember, we're looking at zeros relative to the number, not relative to the decimal point. That's a really important point here. So the very first 2 zeros there are not considered significant, and we'll demonstrate why when we start going through and looking at scientific notation. Lastly, trailing zeros, those at the end of a number, are only significant if there is a decimal point. Doesn't matter where the decimal point is in the number. If there's a decimal point in the number and you have zeros that are trailing non-zero digits, then they will be significant. So for example, 40. It has a trailing zero, the 0 at the end, and there's no decimal point, so that 0 is not considered significant. However, if I put a decimal point there, that makes that 0 significant. So 40 with a decimal point would have 2 significant figures, and 40.0 would have 3 significant figures. So again, it does take some time to understand how we go through and evaluate significant figures, but as you continue to practice with it, you recognize that really the only tricky part is figuring out if the zeros are significant or not significant. Big thing here, 3 and 4. Leading zeros, numbers at the beginning of a number, zeros at the beginning of a number are never significant. Trailing zeros are significant only if there is a decimal point in the number. So here are some other rules with significant figures. We take a look here. We have a number down here at the bottom, 0.007, 000, 2000. The zeros that are leading the number are not significant. The 7 is, and the 3 zeros that are in between the 7 and 2 are also considered significant. The 3 zeros at the end are also considered significant because there is a decimal point somewhere in the number. Again, where that decimal point is located is irrelevant. It's simply based off the fact that there is a decimal point within that number. So follow these rules and you'll easily be able to determine the number of significant figures in any given number. Which is exactly what I'm going to have you do here. Take a few minutes, pause the video, we'll come back and I will go through and tell you the number of significant figures in each of the numbers that are listed on this slide. So hopefully you went through and evaluated each of these numbers based off of the number of significant figures each one has. So if we take a look at the first number here, we have 4 non-zero digits, all of them significant. We have zeros at the end of the number. Trailing zeros are significant if there's a decimal point. It's going to have 6 significant figures. Second one down here, we have a 3 and a 1. Both of those are significant. We have leading zeros, and remember that leading zeros are never significant. So this one just has 2 significant figures. The next number, 97,200, has 3 non-zero digits. We have trailing zeros, but there is no decimal point, so they are not significant. So we have 3 sig figs. 637, 3 non-zero digits, all of them significant, so 3. 620 with no decimal point is 2. 620 with the decimal point is 3. Remember, that decimal point makes that trailing zero significant. 620 with an extra 0, again, all 4 of those digits are significant. Trailing zeros are significant if there is a decimal point. Let's look at the next number, 0.00340. You have 3 leading zeros that are never significant, a 3 and a 4, and then a trailing 0, and that trailing 0 is significant because there is a decimal point. So 3, 4, and 0 are significant. We have 3 sig figs. 10, we have 1 non-zero digit and a 0 at the end. Trailing zeros are not significant if there is not a decimal point, so just 1. 0.0003430. You have 3 non-zero digits and 2 trailing zeros that are significant because there's a decimal point, so 5. 3, 4, and 9 are non-zeros. You also have a 0 that's in between 2 non-zero digits, so that means that it has 4 significant figures and 1 has 1. So again, just continue practicing with those. Go through and remind yourself of the rules. Make sure that you practice with the rules because again, they become very important when we go through and round our math to appropriate significant figures.